Right. So now, we'll actually give you three different semantic views for our workflow language. Of course, they are consistent with each other. I wouldn't really address how we actually prove the consistency between the three semantic views. I'll just introduce the important properties of the operators. And for the rest of the details, I would encourage you to read my paper. Right? So first of all, we give the operational semantics of our workflow language as a collection of transition rules. The first one is for the action prefix. And the thing to keep in mind is there should always exist a valid binding with respect to the relational semantics of the action A. And more precisely, the before binding, B, without a prime, has to be a member of the precondition of the relational semantics of A. And the after binding, B prime, has to be a member of the relational image of the before binding B. So we're going to make sure this is really a valid execution instance. And the domain of the environment wouldn't change because we haven't declared any new variable. So this is actually the most important rule for our semantics, because this is really how our workflow language stands out as opposed to CSP. The next one I want to introduce you to is the parallel composition. Our parallel composition is actually similar to the interleaving operator in CSP, which means we do not do any synchronization on events. What we actually do is to say, for the parallel composition to proceed, we just need to execute an event from one of the two workflows, either from W1 or W2. There's no synchronization whatsoever. And the next one I want to introduce to you is for the guarded workflow. So here you can see we have a guard G and we have a workflow W. And to actually be able to execute W, the current state must satisfy the execution instance B and B prime, as I just said before, has to satisfy the guard G. Otherwise, you couldn't really execute W. And one point to keep in mind is our guard G here constrains only the next operations of the workflow, only the next operation. It doesn't really distribute through all the operators. I'll actually show you for some operators, the guard operator doesn't really distribute through. Right, so that's for the operational semantics. I have introduced you for the three operators. As for the trace semantics, or the denotational semantics, we will actually define a semantic function that will actually map the workflow into its behavior. And the behavior is defined as a set of traces. And we actually go over also the three operators we have just gone over for the operational semantics. And for this action prefix, it's pretty similar as before. So what we have to make sure is the execution instance has to respect the relational semantics of A. One thing that we have to really be careful is interference is really possible between executing A and executing W. Anything might just happen between A and W. So we really allow concurrency to happen between A and W. The next one, again, is the parallel composition. As I just mentioned, it's similar to the CSP interleaving operator. And so to actually calculate the trace for W1 in parallel with W2, we just have to calculate the set of traces by interleaving W1 and W2 because there's no synchronization. I have to stress the point again. Next one is about the guard operator. As I just mentioned before, the guard operator only constrains the next operation in the workflow. So it will make sense to define this operator, the trace semantics for this operator, by considering a special case. As you can see here, G and A, we call this the guarded action. So this is an action with the guard G. So we will take this guarded action and put it in the scenario of action prefix, which means in order to execute W, you have to execute A first. But before you execute A, you got to make sure the execution binding instance has to satisfy the guard G. And this is how we define the semantics of this construct. And it's no surprise, we have to make sure two things. The first, we have to make sure the execution binding respect the relational semantics of A, and also the execution instance has to respect the .g. Right. So we have so far defined the operational semantics and the denotational semantics. So now I will present the third semantics, which is called algebraic semantics. I'll just give you some laws about rewriting the workflow patterns. So first of all, let's do a couple of properties on the God operators. So first of all, if we have several consecutive instances of the God constraint, we can actually conjoin them into a single one. That's what the first one is saying. The second one says the God operator wouldn't make any difference to the deadlock process because there wouldn't be any action to be performed anyway. And as I just mentioned in the previous slides, the God operator distributes through only some operators, not all. So one of the operators that he distributes through is the choice operator, which means if you want to constrain the choice between two workflows, it's like you're constraining on individual ones. Now, this slide is actually more interesting than the previous one. So the God operator doesn't actually distribute through the parallel composition, and it doesn't distribute through the sequential composition either. Why? Let's have a look. For the parallel composition, let's just consider two workflows here. So the first one, you can see the God operator is at the top level, constrained the top level of a parallel composition. In the second case, the God operator actually distributes through a parallel composition for the both operands. And let's consider a trace of executing A1 after A2. For the first workflow pattern, if you want to execute A1, you better satisfy G first. However, after A1 is executed, you don't really have to satisfy A2. You don't have to satisfy G in order to execute A2. On the other hand, for the second workflow pattern, to execute A1, you better satisfy G first. However, to actually execute A2 after A1, you have to satisfy G again. So you can see the subtle difference between these two workflow patterns. So it doesn't really distribute through the parallel composition. And it doesn't distribute through the sequential composition either, because G will actually only constrain upon the first event of W1, and it will only constrain the first operation of W2 if W1 has already successfully completed. Like a skip.
Maybe go back to the question. Here the distributivity does not hold for parallel composition. It could be up to the interpretation of what semantics do you choose for this parallel composition. If you there seems to be a difference between who is making the choice. So if you are prepared that you need to cope with two possibilities, and in the semantics you take care of that.
Yeah, I see your point. So basically what I'm showing here is just one scenario where the two workflow patterns are not equal, are actually not the same. Of course, the user has to make a choice whether to execute A2 first or A1 first to complete the whole workflows. But this is actually not a formal proof for the inequality between the two workflow patterns. I'm just showing you one scenario where the two cannot be equal. So overall, cannot be equal either, of course. Okay, yeah. We can talk about this offline.